Tuesday, we're reviewing the May 2016 final. On Thursday, we will go over the problems for tests 1, 2, and 3 of this semester. The Friday tutorial at 2:30 here will be, we're going to do the other final from the other summer, I think. The other one that I posted online. And then we're good to go.
How much bonus points did you decide to give us?
I have decided, but I'm very I will say this. One, I'm very content that the Chancellor retweeted my post. There have been over, I think, 1,800 views on YouTube of that video. Thank you, popular. So I'm content. I don't know specifically what it's gonna be. Could it be a test bonus? Could it be an increase across the board on your final grade? I haven't decided. So, but bottom line, I'm a happy professor because of that. So, especially with the Chancellor. Yes. Test 3. Are we talking about the curve for test 2 or 3? Hold on, I think. Alright, I'll talk about that test on Thursday. I don't think it is an extreme violation. I think it's a subtle violation. I think the happy squirt, in fact, makes the problem easier. The quirk, most of the 2 other versions, they had to do all this power slugging. With the quirky version, it's like x2 equals 5 9 x1. You can't do a solution for that with whole numbers. Trying to think of this. Oh, the most popular person in the room is your dog. Congratulations for him winning the dog. So, I think that's it. Before we really get started, you guys are 214s, you've been through the drill. I've got to say this now, I'm going to say it at the final. For those of you who have never taken me before, there is method to my madness. When you take the final here, 1 week from today, at this very moment, when you finish the final at 11 o'clock, you're given 1 hour to make sure you're outside Lewis Hall. That is because I need to grade. And I need to grade this class, the other class, all the labs. Your TAs are running wild. I have to rein them in and curve those labs. And yes, I'm curving all the labs. I would say, here's the bottom line. If the average for the lab is over an 88, or even more, there have been some labs where it's a 93, and I go, no, that's not happening. But if your lab is like a 72, everybody. So it's, for those of you in BBs, John Ross, all those mean TAs, they're going to get fixed. But after that hour passes, if I see you on campus, outside of that building, everything's fine. I'll give you a slight nod and move on. But if I catch you inside, outside my office, looking into my office when I'm there, looking into my office when I'm not there, if you're in an alternate reality in my office, any of the lists, there's a whole file where one sheet is this disclaimer of everything you cannot do. And if you violate the rules by basically going, Dr. Eschenberg, your child's real hard. Dr. Eschenberg, how are the finals being graded? You're allowed to do that. But the price for doing that is 200 points off your final. Question, does that mean I could get a negative score on my final? Yes. So what does that mean? All you have to do is stay out of that place. Today, tomorrow, through Monday, I will be happy to address grading concerns like, I don't think you added up the test right, the problem sets weren't added up correctly, is this number in the book? I am very happy and motivated to get that stuff done. Once you get done with the final, do nothing. Stay away from me. Write me emails later. What's going to happen is I'll turn in the grades the Monday after finals at about 5 o'clock. Grades will be posted around 9 o'clock. And then you can email me. I will not answer that week. I understand we've had a great relationship and friendship so far, but I don't want to talk to any of you. I'm going to take a week off, just like you are. The following week, I'll start answering emails, confirming final grades and stuff like that. If you still have an issue, come see me and we'll talk about it. Time is short, time is valuable. I'm trying to make the best grade or the best evaluation of your grade to go on the final grade. I submit now 2 or 3 grade corrections, basically now it's a year. So I really work hard to make this stuff work right. I even tack on a few points extra just to keep the groaning at a minimum. So if there's a problem, we have the whole summer to fix this if there was really a mistake. So I need you guys, after that final, to not bother me. Because if you bother me, I will A, fail you, and B, I'm going to fail you again. So that's it. Any questions? What we're going to do now is just talk about finals. All right. It's very interesting to look at a final from like 5 years ago. The front page is effectively blank. Now it looks like a contract for a mortgage or something. The rules that I talked about for the final are these. Read this. Basically, it's to stress the point, do not see me after the final. So page 3, I've slapped together all the different equations that I can think of. Huh? So blurry? I know, I'll fix it. So what we're gonna do now, so we're gonna go through this. Oh wait, huh? This is, good question. It's a spring. Now let's, first what I wanna do is I wanna outline the final. So a test is 1 hour, 15 minutes. A final is 3 hours. So we're dealing with something that is roughly, it's more than double and change on top. A test has 25 multiple choice, final has 50. A test has 1 appetizer. A final has 2 appetizers. A test has 3 problems. A final has 6. So effectively, the size of the final is 2 times that of the test. The time that you get is more than twice that of the test, so you get a little bit of more extra time for the test. The test is typically over one section. The final is all three sections, i.e. comprehensive. Now, the interesting thing about 214 is that 213 knowledge will be used. You've seen that as in T2 used rotational motion. T1 used linear motion. And vectors. So stuff like that. Will buoyancy problems and fluid problems be on the test 3? I don't think so. That's just creepy. But, huh? I'm working hard on an Atwoods. I mean, when you think Eschenberg, you think Atwoods. Or vector addition for sure. I haven't figured out how an Atwoods machine would get into this. Well, don't make me think about it. Oh. Scroll down. So let's talk about, before we get into the final, hold on. There are some tests, or some test questions which will be you think you're getting out of here without having to add one less vector? No, I'm not talking to you over on the side. Don't look at him, he's self-conscious. You're gonna add a vector. You're gonna add E fields, you're gonna add forces, you're gonna add magnetic fields, you're gonna add something where you're going to have to go through the identify your vectors in polar notation, break them down into component form, recombine them into a polar vector, which is the sum of the vectors. It's a final. I don't think we'll have to work with an equilibrium. Just the resultant would be fine. And this is something where this particular list, what I'm really doing is I'm putting together my outline for the final, really. Compound lens. The 1/3 of test 3 that I did grade and add up, there were, I felt that the average is going to be high. I think the average is definitely going to be in the mid-80s, around 85. There were quite a few 99s, which fills joy in my heart because, or fills my heart with joy because I can handle 99s. I can't handle perfection. So just think of a 99 as 100 in Eschenberg's class and you'll be fine. Compound lens is going to be on this test. I thought you guys did great with the lenses and mirrors, so we'll probably do something like this. Vector addition tends to trip everybody up in the first test, so your guys are going to see it again. Namely, things that I have not specifically covered in tests and I think are still interesting will go on the final. Circuit analysis. Basically, given a circuit filled with resistors and a battery, give me equivalent resistance
I naught, and a potential at a specific point. Pretty much exactly what you did in test 1. And so that will definitely be in. Magnetic fields. Oh. There's a part of me Faraday's law. And just to give you fair warning, in previous finals, I typically cover the one that isn't on test 2. Question. Richard.
Number 1, would vector addition be E-field addition or A-field addition or B-field?
I don't know.
Okay.
I'll roll a die.
Number 2, would it be a constant change line or a convex line?
Well, the compound lens, it's going to be a lot like glass. You're going to have a concave and a convex. There's a series of letters that are available to me to make unknown. And then, I'll ask you for it to solve. Now, one of the things I will say this, with test 3, test 3's tests in general are typically written the day before, like at night, and I'm freaking out. I'm trying to make it quick. The final, I'm gonna write over the weekend, and I'm gonna spend 2 days alone with your final. Polish it, smooth it, make sure everything works. There will not be any unforeseen accidents like what happened with that. And because this file is going to be written in my Fortress of Solitude, and ain't nobody going to get in there to bother me. So, it will be resistors only with a battery. So it's well, that's a different type of knowledge. I haven't decided. Faraday's law, the big reveal. Most likely, the bar will be a problem again, and the circle will be an appetizer. You're gonna get 2. So one of the appetizers is taken. Lower probability, like for Faraday's law, circuit analysis, compound lens, and vector addition, those things are rock solid. Those things are metaphysical certainties. A lower probability, thin film, single slit, double slit, diffraction grating. I felt that you guys did okay with that. Really, how I write finals is I'll write like 5 appetizers and 12 problems. And obviously you're not going to get 12 problems, you're going to get 6. And you're not going to get 5 appetizers, you're only going to get 2. I keep asking for an 8-hour final, but they just won't give it to me. So I got to fit it within the time. Yes? Did I do what? We did some, just maximum and angle. And honestly, a diffraction grading would be multiple choice, appetizer at best. So it's not, that's why I say lower probability. Like I'd have to go there and go, that's awesome. And then one, yeah, I'd use one of those. I'd pick that. Know the basics. I definitely know the basics. Single slit min only. Double slit, max and min. Diffraction grading, max only. Know those big differences. Know what small angle approximation. Know that you can go from sine theta to tan theta to L over L. That kind of thing. Let me look through the problems real quick just to see if I missed anything. No. Right hand rule game, no. I will say that the right hand rule will be used. You're going to have to figure out. So, like with vector addition, the vector addition is going to be angles that are going to be at different angles. There could be at lower B field addition where given a series of currents, determine the B field at a specific point. Something like that. One of the things that I do is, like on Thursday, I plan on going through tests 1, 2, and 3 in front of you guys, writing out the solutions, talking about the pros and cons of each problem, stuff like that. The thing that, and on the side, I'll do the multiple choice and release that, and so you'll have all the versions of all the tests, and we'll be happy. That may not happen this week. It may happen over the weekend as I go through it. The tests that we took this semester. 1, 2, and 3 of spring 17 will be done on Thursday. Circular motion, the particle spectrometer. Will be in it. No, I take that back. I'm not saying will be in it. I'll say it's a really good shot at it. Oh, because before I answered your question, I was in the middle of a soliloquy. So I'll have 12 problems and 5 appetizers. And what I'll do is it's a lot like growing plants from seed. You plant the seeds, sprinkle a little water, set them out in the sun, and they start growing. And there's always that one seed that just looks like a total mutant. What do? You yank that seed out, you let the others grow. So I look at the problems on Thursday, I'm going to go through all the tests, and there will be things that I go, that's kind of boring, or you guys did great on it, or B, this looks interesting. And so what I'm going over through in my head are the tests, the final. So pay attention on Thursday and how I say them.
Are you going to have it written over?
No, I'm not. Oh, no, I'm gonna have it written over the weekend. Probably what will happen is I'll write it over the weekend, proof it on Sunday, and then print it Monday. So then probably by Monday afternoon, I'll be a little bit friendly to actually maybe perhaps help people with physics, but by then I'll have 380 people with a final the next day, so chances of getting me are going to be pretty slim. Yes? That's a good question. I definitely put it on the table. Now we can see where the problem's coming, because the circuit analysis problem, I would say, is a de facto certainty. Circuit analysis, de facto certainty, metaphysical certainty, yeah. Particle spectrometer, where you've got E squared over R. where the particle comes out, it is Bose, because it's moving in a charged particle in a moving charged particle in a magnetic field and parts. Kirchhoff's law. You guys didn't do great on it. Some people did, other people don't. If it ends up in a case where I've got an available 1 of 6 problems available, Kirchhoff's law is definitely on the list. I would definitely know it. Just be able to rattle that off. It's less probable than a circuit analysis. Circuit analysis is definitely. RC circuits could be on it. RC circuits could be a very definite appetite. So let's write this down. Because basically I'm writing this for my benefit. Hold on just a second. So what's your question? Polarization film? I'm not feeling it. I mean, it would really have to stand out to me and going, yeah. I mean, a lot of people just nail it. So I'm feeling very lower motivation to put it on the fence. Particle motion, well, that's kind of like particle spectrometer. But the thing that when I'm talking about particle motion is, and this is where you have to understand the equations of motion. Charged particle in an electric field, I drop it. Where does it land? When does it land? What is its final velocity when it lands? Stuff like that. That would be a particle, or that would be a good last question. So already we're at 10, and I'm only going to be able to put up 8. So there's going to be stuff that kind of gets merged together or not included. There just isn't enough time to do that. If it was an 8-hour final, yeah, everything would be on the final, but no, it's only 3 hours. I write the final twice as long as a test. So that makes it 2.5 hours. It's a 3-hour final. That gives you an extra 30 minutes to review your answers. And, but we will start on time. Most likely there'll be an extra 5-10 minutes tacked on to the back end. And I'll still be trying to pry the final out of your fingers when the time's over. But it's a legitimate test for a normal student, 2.5 hours, get in, get out. General philosophy on the final grade of the semester. I think that there are people who are upset that my average for 214 in the spring is not a B minus. Most of the time it's a B to a B plus. And why is that? Because the room is filled with provost and honors students and pre-med students. We've bled out all the, no offense if you're in exercise science, but the vast majority of your associates have already left. So it's a much stronger class. The academic ability of the class is far higher. That's why the average of this test tends to be, or of the whole class is a B, at least. Lab grades, I'm planning on the average being an 85 to an 87. That's what I want. So if it's below an 85, 87, just boost it up. If it's higher than that, then cut off. And yeah. All right. We ready to dive into a final? Yes.
So this is the most that you can pull anything just randomly.
I can pull stuff from anything that I've talked about in the class is game.
But the basic problems.
But the basic problems, yes. Yeah. Oh goodness. Two capacitors in parallel. Oh, this one's easy. One of the capacitors doubles its capacitance, the other one does not change. What happens to the equivalent capacitance of the circuit? It increases. What happens to parallel capacitors in parallel? You just add them. So if you add them and one of them increases, then the whole thing increases. Unit for frequency is what? Hertz. If I said inverse of frequency, it would be what? Second. In Brevard Hall, you let go of a negative particle that has a mass of 3 grams. It sits there. It moves nothing. In which direction is the electric field? A, ceiling to floor. The particle wants to go down, but the electric particle, or the electric forces, make it want to go up. The only way that a negative particle wants to go up is if the E field is in that direction. Magnification is -2. Your image is inverted and enlarged. The fact that it's negative means that it's what? It's inverted. The fact that its magnitude is greater than 1 means that it's enlarged. The dark spot in a single slit pattern is when blank occurs. What is blank? Destructive interference. A positive particle moves from left to right. It accelerates. What is the direction of the electric field? Left to right. Object in translational equilibrium means what? Sum of the forces is equal to 0. Rotational equilibrium? I don't know. Probably not. I can't think of anything right offhand that I would like rotational equilibrium. Oh, well, I do. I think you just have to know it. I think, initially I was thinking, will I do a problem with it? No. Smallest index of refraction is what? A, 1. By definition, what is the index of refraction? Speed of light over the velocity of whatever that light's doing in a medium. Yeah. Rotational equilibrium, E. When charging items through conduction, which particles move? The electrons. If current is going from left to right, electrons are going right to left. Electron flow is opposite of current. You have a lens diverging 8 diopters. The focal length is what? -12.5. The fact that I said diverging lens means that the focal length is negative. That 8D is the strength of the lens, which is diopters, inverse diopter, inverse meters. So we get -12.5. Convert 2 nanometers into meters. Oh, this one's nonsensical. I ended up having, so in a vacuum, will this now be fill in the blank? Light's wavelength is 500 nanometers. It passes into glass. The index of refraction is 2. What is the new wavelength? 250. Question, light's wavelength is 500 nanometers. What is its frequency? And it's 500 nanometers in a vacuum. So wavelength times frequency is velocity. Frequency is velocity over wavelength. So 3 times 10 to the 8th over 500 times 10 to the -9. 6 times 10 to the 14 hertz. So if it's 6 times 10 to the 14 hertz in vacuum, what is it in the glass? The same. Frequency never changes. Particle spins around a circle n times in t seconds. What is its frequency? It's just n over the total time. So it is E. What kind of problem would come from this? Just a simple charged particle in a magnetic field and it spins around in a circle. And so I could ask you questions about, well, what's the radius of the circle? What's the linear momentum of the particle? What's the period of the circle? Stuff like that. Now, some of these are rather basic. Some of these I look at and go, I may not do this. What are the units for velocity? D. C represents units for what? Acceleration. 16. Now these I've taken out. I had a professor tell me that stuff's easy, it's obvious. And I'm like, oh, sometimes I catch people who don't know what that is. That is a vector doing what? Pointing into the page. And I was so happy when I went to the MSMS interview because they did have 2 rulers and I did Faraday's law with the moving bar. So of course I had to initiate them with the magic imaginary bow and arrow. So they learned. Momentum is the product of what 2 quantities? Mass and velocity. Ideal voltmeter has a resistance of ideal. Ideal voltmeters are the perfect voltmeters. Infinite. Now, when I say, let's say I said non-ideal voltmeter, which is realistic, it's D. Now, when I say ideal or non-ideal voltmeter, I mean a reasonably functioning voltmeter, so 10 mega ohms. You could have a voltmeter of only 10 ohms, but that would be a very poorly constructed voltmeter. Yeah, it's voltmeters at Ole Miss, 10 mega ohms. Voltmeters at State, 10 ohms. There is a difference.
That'd be the non-ideal ammeter.
The non-ideal would be 10 mega ohms.
But the ammeter.
Oh, ammeter. Ideal ammeter is what? 0. Non-ideal, very functional ammeter. 10. Close. The one closest to 0. Which of the following is the smallest? Nanometer. Which one's the biggest? E, kilometer. Your image distance is -6 centimeters. Your image is virtual. Virtual images are to the left or right of a mirror. To the right. Virtual images are left to right of a lens. Left. Because we're doing the compound lens problem, and I strongly don't think we'll have the singular lens or mirror on the final, we will not be doing ray diagrams. So don't worry about that. I still, just as a recommendation, pens, pencils, erasers, markers, highlighters, all the colors that you can think of allowed in the final. Calculator in the final. Green Scantron in the final. And if you want to bring one, a ruler. Because I do like straight lines. I cannot tell you how good penmanship makes me happy. And so if you're gonna learn how to write your name in block letters, that would make me really happy. Most of you do a good job, others, not so much. Concave lenses are known as diverging. Units of radial acceleration, A sub r, is what? It's E. If it was angular acceleration, it would be blank over inverse seconds, or blank over second squared. So alpha is this. AR, which is the common A, is that. Two capacitors are in parallel. Which of the following is true? So parallel means they're like this. It's B. Oh no, I'm sorry, take it back. It's E. The potential difference across that one is the same as that one. So it has to be E. 2 meters at 100 degrees is what? Second quadrant. Stuff like that. Yeah, when I'm going through this, one of the things that I may want to do over the weekend is purge out the ones that I think are primarily 213. If it's like this, I would go, if I've got other multiple choice questions, I'll put those in. Yeah, I would look at the ones for the test. Yes. 23 E. Because the one thing that I've started noticing with my my multiple choice set banks, they're getting big, which means I can start eliminating the problems that I think are either repetitive or just not. I mean, some of them just get obsolete. Double slit experiment, DL over big L, M lambda. As little d goes down, the distance from the central max does what? So if little d decreases, to keep this constant, little l increases. Which is not an expression for the units of force, C. Like this is a torque problem, really. Not sure if I'm going to have that in. Frequency is 2 hertz. Angular velocity is 4 pi. 1 rotation, 2 pi. 2 rotations, 4 pi. Concave mirrors are what? Converging mirrors. Unit for period, second. Oh my goodness, they ate this up. I'll fix this. I know you guys don't want it, but radial acceleration is v squared over r. Angular velocity, v is equal to omega r. And that will be something that I'll have to pay attention to and make sure it's on the test. How do I get what? From frequency? Oh.
Is this going to be on the fact sheet?
Yes. And it'll have to be something that I remember. And if I don't put it on the equation sheet, tell me to put it up on the board. I think it's a valid equation. Okay. Capacitor plates increase in area only. Does the capacitance, what happens to the capacitance? It increases. Single slit experiment, increasing L, big L, the distance from the slit to the screen. So big D, LL Huh?
Now, the problem is
If big L increases, then little l. Whoa. Oh, decreasing the distance. If big L gets smaller, little l must get smaller to compensate. Joule unit of energy. 35, I messed it up, so I just gave, no, this I intentionally did. I put in a fluids problem and I said, how did that get in there? So I just gave him the answer and said, the answer's A. Enjoy the points. This I will eliminate from the final. The M equals 1 minima, that's just extraneous information. Really all I'm looking for is the fact that little l decreases when big L decreases to maintain the ratio. The whatever order of the label for the specific minima that I'm interested in. No. M equals 1 was a dead end for that problem. Unpolarized light goes through a single filter, 1/2 I naught. Non-ideal voltmeters. Skip 37. Tau in the charging of a capacitor equation is RC. Single slit experiment, which of the following is true? E. Studying a plot of current in a circuit as a function of potential. Across that circuit, the slope of the line is what? Inverse of resistance. Ohms multiplied by farads is what? Seconds. The bright spot on a single slit pattern is where what occurs? Constructive interference. Non-ideal ammeter. Induced flux is always opposite of the change in flux is what law? Lens. You are spear fishing. You look down into the river and see a 10-pound bass. A successful spearing requires you to aim below, because the light from the fish will bend out further and you see the virtual fish there when the real fish is there. So you aim below. Light in water travels slower than light in a vacuum. What are the units of magnetic flux? D, Tesla meter squared. Rubbing silk on a glass rod makes the rod. I know, I love that one. Convex lenses are known as converging lenses. Light passes from water to glass. Which of the following is false? B, frequency changes. Huh? What? I think the version is the particle. Because I think, huh? Yeah. So in the version is electron that we're doing. It's from the spring 2016 final. What? I can't read lips. I'm sorry. Oh, bonus points? No, it's full enough. Okay. We're going to push as far as we can. Anything we don't get finished with, we'll We're not going to do a final in the next 15 minutes or 20 minutes at that. All right, first problem. An electron is moving in a circle in the B field. What's the period? So M, you've got M and Q, V is given, B is given. So the sum of the forces, because it's a circular orbit, is mv squared over r. A charged particle moving in a field is qvb. So circular motion is this, the force is this, so you set each one to each other. Now, the one thing that I did not give you was the radius. However, I do give you, you do know that circumference is 2 pi r. And that the period, the total time, is the distance circumference divided by the velocity. So the velocity is circumference divided by period, or you could say it's 2 pi r divided by the period, and that is equal to velocity. So you plug this into V right there. So M 2 pi r over r period is equal to QB. R's cancel. So 2 pi m over QB is equal to period. Done. And so that's how you get it. Now you just plug and chug. You keep the you use magnitudes only for this because I'm only interested in the time. Appetizer 2. Given the charge listed, you've got a positive 3 at 6 negative 2 microcoulombs. You've got a negative 5 at, or actually I messed that up. Hold on. Positive 6, negative 2 is charge 1, which is positive 3 microcoulombs. Negative 2, negative 4 is a negative 5 microcoulomb charge. I'm looking at the potential of 3, 5. So the total potential, I'm sorry, is V1 plus V2. V1, oh yeah, hold on. V1 is KQ1 over R1, KQ2 over R2. That is R2, that is R1. So delta X1, the change in X is 3. The change in, oh, I take this back. This is delta Y1. The change in Y, I go from negative 2 to 5 is 7. And these are all in millimeters. So K is 9, 10 to the 9th. Q1, 3 times 10 to the negative 6th. And R1 is 7 times 10 to, or I'm going to use 0.007 squared plus 0.003 squared, square rooted, or summed and square rooted. That's the first one. And then the second charge is negative, so it's negative 9 times 10 to the 9th, 5 times 10 to the negative 6, square root. The change in x2 is, no, that's change y2. This is change in x2. Change in x2, I go from -2 to 3, so 5 millimeters. Y2, I'm going from -4 to 5, so that is 9 millimeters. So this is 0.003 squared plus 0.009 squared. Could be positive, could be negative. And then you just add them up.
You went there instead of 5.
Oh, did I use the wrong things? All right, hold on. So for x2 to the point, or from point 2 to the point, x2 goes from -2 to 3, which is 5. So yeah, that's 0.005. Does that fix it, or is there something else? That fixes it? Good. Then all you do is add it up. Now for the problems. Problem 1 is like the diamond RC circuit from, or the C equivalent problem back in problem set 3-ish, I think. We covered something a lot like this. The now here, those circular blocks, those two are identical and those two are identical. So if I figure out what this is, I can figure out what that is, and then I just mush them together. So for those two, in the upper one, oh, I know, I need to back out. In the upper one, I've got 4, 1, 1, 2. Here, 3 and 3. All have the C's. So the first one, I'm going to smoosh 3 and 3, those 3's, and the 1 and the 2 to get me this. Now 3 parallel with the 3 is a 6, C. A 1 series with the 2 is 1 over C plus 1 over 2C inverted. Common factor 2C, 2 plus 1 is 3 over 2C, or 2C over 3. So this is, huh?
The middle one on the first one.
Yeah, so 2C over 3, a C, and a 4C. That's not focusing as well as I'd like. Now those are all, you add them together. Zoom out. Yeah. 2C, or 2/3 C, 1C, which is C, and 4C is 5. 5 times 3 is 15, plus 2C is 17C over 3. And now the equivalent circuit of the upper band is 3 over 17C plus 1 over 6C inverted. (102/35C). That's just the upper. The C equivalent is 2 times 102/35 because you're just adding them up. So it's 204/35C. Now, one of the things that I did was I gave you the value of C. You didn't think I would leave him out, hang him out to dry with a very weird fraction. If C is 35 nanofarads, the equivalent capacitance is 204 nanofarads. Now, if the equivalent capacitance is 204 times 10 to the negative 9, and the resistance is 20 times 10 to the 6th, my time constant, tau, is 4.08 seconds. Because tau is equal to RC. Now, if I charge this thing up, yes?
I got it here. In the first step, I had 3 capacitors, or I'm sorry, 2 capacitors. That's the difference. 2 3 capacitors over 2. Yeah. What's 3 plus 3? Resistors in parallel, you got that weird inverse. Capacitors in parallel.
That shouldn't be in there.
So if you have more than one resistor, would you smush them all together and then
Depends on the situation. If I had, I think the question is that poorly phrased. If I have more than one resistor, you just do the equivalent of what I did.
Yeah,
You
so-
find regions which you can smush them together until you get one resistor.
So tau is R equivalent times C.
Mm-hmm. Well, in this case, it's R because it is given to you times C equivalent, because we're figuring out what that C is. This is a charging equation. We're looking for 80% of maximum charge. Because they're exactly the same. Yeah, because the upper one is in parallel with the lower one, and both of them have 102/35C, you just add them up. Because this one is in parallel with that one. Yeah, this is the last problem we're doing today.
How could you tell that it's charging?
How can I tell that it's what?
Charging.
Because I think, how long would it take for the capacitors to reach 80% of their maximum charge? I think it would be a fair question to ask, is it charging or discharging? To clarify, I would then answer to say it's charging. And so that would be the answer. So it's a combination of an equivalent capacitance problem with a very simple RC problem attached to it. Pretty legitimate in terms of what's on the final. That's all the time we've got. We're gonna finish this, do the test problems or as much as we can on Thursday, and then wrap it up with the final review on Friday.